So, hi everyone, welcome back to Eliki. So, today we're going to see actually how to calculate the pH of the mixture. So, this section of acid and base requires a lot of calculation. So, we'll take a small example in this case. Take a small example. Calculate the pH of the mixture of kidney. When Nixon, we'll go one more now. 60 centimeters. Ici. And open 5 more. 40 centimeters. So you might have that. So in this case, in our calculation, we are calculating the pH of a mixture. So pH of the mixture. pH of the mixture. So the mixture in this case now is a mixture of sodium hydroxide and hydrochloric acid. So let's take our calculator. When such question is given, the first thing to do is to look for the number of moles of the acids and number of moles of the base. So let's listen. N acid equals to C acid, G acid. C acid is the concentration of the acid, 0.1. The volume of the acid, 6 divided by 1. We divide 1 out because 1 convert your volume of CMP to DMP. We have score for the calculator, delta 1 by 60. And 6 gram malaria. Look the little 6 move. Also calculate number of moves in base. N base equal to C days, D days. The concentration of the base is 0.2. The volume of the base is 40. Divided by go. N base equal to 0.5 times 40 will be 20. Divided by 1000. We will leave it 0.2. 0.02 mole. We realize that the number of moles on the base is higher than that of the acids. So M base is greater than N acids. The solution is limit. So I'm going to calculate the excess number of moles on base. The excess number of moles of the base is the number of moles of the base minus the number of moles of the acids. It's going to be 0.02 minus 0.002. It was find the with basics. Because it's 0.014. So we need to know now to calculate the number of moles of the base found in the mixture. So the concentration of the base out of the mixture, which is the excess number of moles of the base, because as neutralization, an amount of acid will neutralize another amount of base. So this is the excess number of moles of the base inside the mixture. Want to know that the concentration of that excess moles in the mixture. So the concentration of the excess mole is 0.01. Because concentration is the number of moles of the volume. All over the total volume. The total volume in this case we are going to add 40 and 60. So having 40 plus 60, which is 100 cm cube, we divide by 1000. Because don't forget, concentration is the number of moles on the body. We have the number of moles on the body. This volume V total is 60 plus 40, which is 100 CNT. Is GMQ will give us 0.1 molar. DMPQ. Because I can calculate the volume because the total volume is 60 plus 40 with 100. So having 100 divided by 1000 because we want to convert the volume from CNQ to DMQ, which will give us 0.1. Swing line of the base because we point from 0.1, 0.014 divided by 0.1. So I like it 0.1 kilo. Voilà. So the solution is basic. The first thing to do is that we are going to calculate a pH because I don't want to get no acid was a base. So we're going to calculate the pH. pH is minus of condensation. So minus log of 0.14 Q is sequence. I have to punch. So I have to punch the EOB minus log of 0.4. So I have 0.8. 0.81. The pH is a percent 14 lemmas. Here is minimum 14 minus 0.85. Our pH is the difference 14 minus 0.85. 13.1. So that's how I calculate the pH of the mixture. So now we're going to see, lastly, on topic 2, we're going to see how to calculate the pH of a buffer solution. So a buffer solution. Buffer solution. A buffer solution is a solution whose concentration. A buffer solution is a solution that resists. A buffer solution is a solution, so we have to have the definition. A buffer solution is a solution that resists a change in pH upon addition of a small amount of acids or base. So calculating is the definition of buffer solution, but a buffer solution is the solution that resists a change in pH upon the addition of a small amount of acids or base. So there are two types of buffer, one acidic buffer and one basic buffer. So let's take the first one, acidic. Acidic buffer. In an acidic buffer now, we're going to take an example. So an acidic buffer is made up of a weak acid and a soluble salt of weak acid. So in an acidic buffer, we can take an example, initial of ethylene acids and sodium determinant. So that's the apple of an acidic. So the pH per an acidic nutrient pH is equals to pKa plus log concentration of the salt divided by concentration of the acids. So that's the formula for the buffer solution. For an acidic buffer here, because you see the expression for Ka. So when we talk about an acid, there's an acidic covenant Ka. So for a buffer solution pH or an acidic buffer, pH equals to pTA plus log concentration of the salt divided by the concentration of the acids. So let's take a typical example. So let's take an example. A buffer solution was obtained by mixing 0.1 molar sodium ethanol and 0.2 molar ethanolic acid. pH of the acid phenol basis will bend to the analysis. So let's read the question together. A buffer solution was obtained by mixing 0.1 molar sodium ethanol and 0.2 molar ethanolic acid. The question is stated of calculate the pH. Calculate the pH. Calculate the pH. So let's see how we can solve this exercise. Solution, read about it. So pH is equal to pKa plus log concentration with salt out of concentration with acids. The salt in this case is our solution of sodium ethanol. The acid obviously is a carbonic acid. But we given the Ka of the acids. Given that the Ka of the acid has been given, we want to calculate the pKa. But we want to pKa equals to minus log of K. pKa is minus log 1.6 and then to the next 6. So what you punch here to calculate the value of pKa of function. Yeah, we have minus log. And so I'll go 6 times 3 to 6. 5.7 or 5.8. pH equals to 5.8 plus log the salt. I tell you that the salt is the salt of carbonic acid, only the sodium ethanol. So log of 0.1 divided by 0.2. 0.2 here is the concentration of beta-red acid. So that's to forge log of 0.5 plus 5.6 and then 5.4. He suppose 9.4. And the pH of the buffer. In this case, we clearly see that the buffer is an acidic buffer because the pH is less than higher. So next, we are going to see a buffer solution, an acidic buffer or a basic buffer. Was one of them we'll see was an acidic buffer. The best see a basic buffer. So a basic buffer is you have a weak base and a solid salt of weak base. Let's take a typical example. The basic buffer. A buffer made up of ammonium chloride, ammonia. What a weak base, a ammonia is a weak base. A Lewis base or Borzoi base. What ammonium chloride is a sort of weak base. The weak base in this case is ammonia. Given as a base, we have to calculate the pOH first. After having the pOH, we calculate the pH. Knowing that pH plus pOH is equals to 40. So the first step here is actually doing the formula. pOH is equals to pKb plus log the concentration of the salt all over concentration of the base. Concentration of salt divided by concentration of the base. But actually, we need to take an example there because if I just reach you like this, without solving the example, you will not actually know the use of the formula. So let's solve the formula and example. Example of the calculate and play the pH of the buffer obtained by mixing 0.01 molar ammonium chloride and 0.02 molar 0.02 molar ammonia. Kb equals to 1 times feasible 6. Okay. So let's read the equation together. Calculate the pH of a buffer obtained by mixing 0.01 molar ammonium chloride and 0.02 molar ammonia. Kb equals to 1.6 times 10 to the minus 6. So in this case, we can identify the type of buffer solution. The type of buffer solution is a basic buffer. For a basic buffer, we're having ammonium chloride and ammonia. So we have a weak base and a soluble salt weak base. So given that it's a basic buffer, we're going to make use of the pOH formula. So we have to calculate pOH first. On our pOH, we take 14 minus POP. So apply the formula. pOH equal. The year we can say pH is 14 minus POH. Very better. pH equals 0. So first of all, calculate the pOH. pOH is pKb plus clock concentration of the salt or our concentration of the base. So the pKb is equal to minus log of in. So the minus log of what to why our kb here? So our kb is 1.6 times 10 to the minus 6. 1.6 times 10 to the minus. Is it there was 5 to 8? Because we called this before. Apply the formula of pOH. pOH is equal to 5.8 plus log concentration of the salt. The salt is ammonium chloride salt, which is 0.0 divided by 1, which is for pOH is equals. Let's punch it. Let's punch the pOH. Note and 0.1 is divided by 0.0 equal to 0.5. Log was 0.5.
Yes. Perfectly. So pOH is equal to 5.4 starting point.
It's so that's our pOH value. But we know that pH to 14 minus pOH. So our pH is equals to minus 8.5. So that's the pH for the local solution. So thank you for learning with Edunews, and see you next class for the next topic. Our next topic we are going to see is chemical equilibria and redox equilibria. So the first topic we saw was phase equilibria, acid base equilibria, chemical equilibria, and redox equilibria. So in this series of videos, we'll be seeing the various equilibria. So acid base equilibria. In acid base equilibria, we saw how to calculate the pH of a neutral solution like water using the KW value. Going forward to see how to calculate the pH of a strong acid, a strong base, a weak acid, a weak base, pH of the mixture, and also the pH of buffer solution. Going forward to see a buffer solution is a solution that resists a change in pH upon the addition of small amount of acids or base. Then I get the formula because I told you that there are two types of acidic buffer. There are two types of buffer solution. There's acidic buffer, basic buffer. So I get the formula acidic buffer, which is the pKa plus log quantity of the salt or the acid. Then for basic buffer, there are two things you have to do first. The first you have to do is to calculate the pOH. When you have the pOH, you think now pH is equal to 14 minus pOH. So, thank you for watching. Follow me on EduQs. Stay tuned.